In this example, we're going to be considering a pair of linear transformations. We're going to define the linear transformation T1, taking us from domain R2 into codomain R2. We're going to define that by T1 of xy is going to be 3x minus 4y and x plus 2y for the two components. We'll also define linear transformation T2, takes us from domain R2 into codomain R2. We're going to define that by T2 of xy is equal to y and 2x minus y for the two components. We're going to find the matrices of the compositions of these transformations. Now, there are two methods for this, and we're going to discuss both. So the first one would be to actually find the compositions. Find compositions and interpret as matrices. The other thing that we could do is find the matrices of T1 and T2 and multiply in the appropriate order. So for the transformation T, which is the composition of T2 on T1, I think that's what I would like to analyze first. So with that in mind, for method 1 for T, we'll take a nice generic looking vector in R2, we'll call it xy, and we'll send it first through T1, and then we'll send the result through T2. So the image of xy through T1 is, as we said back up here, this will be 3x minus 4y, and then x plus 2y. Now what T2 does for a transformation is it says the second component of the pre-image will become the first component of the image. So the second component here will become the first component here. And then we do 2 times the first component minus the second component. So 2 times the first component minus the second component. Now when we put that together, first component is just going to stay as x plus 2y. Oops, that shouldn't be parentheses, that should be a comma. Then once we distribute and combine like terms, 2 times 3x minus x will be 5x. Then we'll have minus 8y minus an additional 2y, that'll be minus 10y. Now the matrix of this transformation, which we are referring to as A, that would be a 2 by 2 matrix. The first component gets read right to left, so that's 1x plus 2y, 1x plus 2y, and then the second component is 5x minus 10y. So the matrix of the transformation would be 1, 2, 5, negative 10. Now the alternative way to make this happen is we could identify the matrix A1 of transformation T1 and A2 of transformation T2. And then multiply in the appropriate order. So the matrix for A1, once again, we read right to left through the two components. That's 3x minus 4y, so that'll be 3, negative 4. And then 1x plus 2y, so that'll be 1 and 2. Then for matrix A2, we can interpret the first component as 0x plus 1y, 0x plus 1y, and then the second component as being 2x minus 1y. Now the multiplication associated with these is going to be the same as the order in which we write the transformations. So matrix A is going to wind up being matrix A2 times matrix A1. So A2, that'll be 0, 1, 2, negative 1, multiplied by A1, which is 3, negative 4, 1, 2. And then we multiply. So going across matrix A2 and down matrix A1, 0 times 3 plus 1 times 1. 0 times negative 4 plus 1 times 2. 2 times 3 plus negative 1 times 1. And 2 times negative 4 plus negative 1 times 2. So there you have two different methods for finding the exact same matrix. Now, I don't want to have us stop there because I want to have us find a prime as well. So let's do this. I want to keep some of this information on camera as we're recopying. So for t prime of a nice generic looking vector, this is supposed to be t1 on t2 of xy. And here we want to do the exact same thing as what we just did. So t2 of xy, that was y and then 2x minus y. Now what t1 does to a transformation is it says let's take 3 times the first component minus 4 times the second component. So 3 times y minus 4 times 2x minus y. Then for the second component, we're supposed to do first component plus 2 times the second component. Whole bunch of linear combinations to try to simplify here. Now that we have this copied down, let's recenter this. Once we distribute and combine like terms, for the first component I'm seeing negative 4 times 2x, and that's it for x. Then I see 3y minus 4 times negative y, that'll be plus 7y. Doing the same thing for the second component, 2 times 2x will give us 4x, and then y minus 2y will give us minus y. Interpreting this in terms of a matrix, which we referred to as A prime just a moment ago, the first component is negative 8x plus 7y, and the second component is 4x minus 1y. So really the rows are representing the different components and the columns are representing the coefficients of the variables x and y. Now the alternative way to do this, since we already have the matrices of the transformations, is we could also say that A prime is equal to, we write it in the same order as what we see here, so A1 multiplied by A2. Now from the previous page, we'll put this back on camera. Come on, physics, stop being a dick. There you go. Borrowing these matrices from the previous page, matrix A1 is 3, negative 4, 1, 2. And then matrix A2 is 0, 1, 2, negative 1. And then once again, we can start multiplying these in the typical fashion that we would do. So we do 3 times 0 plus negative 4 times 2, that'll be negative 8. 3 times 1, and then negative 4 times negative 1, that'll be 3 plus 4. Now 1 times 0 plus 2 times 2, and 1 times 1 plus 2 times negative 1. And we wind up getting the same result as what we had gotten by interpreting the composition. So 2 different methods for finding matrices of a composition of transformations.